Okay, I think it's time for us to start this session. So, good afternoon, everyone, and welcome again to Young Statisticians Meet 2021. This is a virtual meet, and this is our fourth session and third academic session. So, the name of this session is Data-Driven Statistical Methods, and we have 3 speakers for this particular session. Let me first introduce the speakers, and then we will request the speakers for their presentation. We have Dr. Arindam Chakraborty, Dr. Kiranmoy Chatterjee, and Dr. Jayabroto Vishwas for this particular session. Dr. Arindam Chakraborty is currently in the Department of Statistics, Vishwabharati University. He completed his PhD from Calcutta University and then did his postdoc from Indiana University School of Medicine. He works in joint modeling of longitudinal and survival data, empirical base, robustness, bioinformatics, and some other parts of biostatistics as well. So, welcome Arindam Chakraborty.
Thank you.
Our next speaker is Dr. Kiranmoy Chatterjee, who is currently in the Department of Statistics, Bidhannagar Government College. He completed his PhD from Indian Statistical Institute, Kolkata. He works in sample survey, official statistics, likelihood-based inference, and many others. So welcome, Kiranmoy. And finally, our third speaker is Dr. Jayabroto Vishwas, who is currently in the Department of Statistics, University of Barwan. Jayabroto completed his PhD from Indian Statistical Institute, Kolkata, and he works in longitudinal data analysis, quantile regression, and Bayesian modeling. So welcome, Jayabroto. So first, I'll request Dr. Arindam Chakraborty. So Arindam, it's your time. And I request all the participants just to remind any questions you have, please write in the chat window. And once the session is over, we'll have the question answer session. So Arindam, it's your time.
Thank you, Kiranmoy. Thank you very much for inviting me. Can you see this?
Yes.
Okay.
Yeah, this is good.
Okay. It's nice to have all the young statisticians together in the same platform. And this is the topic that I want to speak about. It is identifying higher order drug-drug interaction effects using FERS database. So this is the database that is available in FDA. FERS means FDA Adverse Effect Reporting System. So this is a huge data they collect over time, and we try to find the higher order drug-drug interaction effects from this database. So in terms of theory, statistical theory, it might not be that challenging, but tackling the data itself is a big challenge. So when Kiranmoy told me something to speak about something which involves data and the model should be data driven, so I thought that let's discuss this thing. So I'll be very happy if I get some constructive criticisms as well as some suggestions for this thing. So why I'm bothering about these higher order drug-drug interactions? So basically this is nothing but adverse effect. So it is the preconceived notion that, or the common sense it says that if you take multiple drugs, then there is a chance of adverse effect. We sometimes call side effects. So if you have for some diseases like cancer or some complicated diseases, sometimes you have to give multiple drugs at a time. So that creates some problems. We call them as adverse effect. So a drug interaction is basically a reaction between 2 or more drugs, or a drug and food and beverage. So for the timing, we'll just constrain ourselves to the drug-drug interactions only. In medicine, an adverse effect is an undesired harmful effect resulting from a medication or other intervention such as surgery. So it's sometimes called as side effect. So it's something like that whenever we go to a doctor, then they will give some medicine, and for that medicine there will be some side effect. Then we have to take another medicine to tackle that. Then it may result in some side effects. So in a way, it's going on and on and on. So identifying this adverse effect or the drug combinations which causes this which cause this adverse effect is very important, so that some guidelines can be provided to the doctors that which combinations are more lethal in terms of adverse effect. And we know that we have a lot of adverse effects, but for my research work, I just choose myopathy as the adverse effect that for this discussion. So what is myopathy basically? It's a rapid destruction of skeletal muscle, and this is if you see the frequency, it's quite high, and this myopathy is believed to this happens due to this side effects of different drugs. So among 7 million FDA spontaneous adverse effect cases reporting from 2001 to 2010, and you will see the number 100,000 are concerned with myopathy. So this number is quite high, and among these 1,634 FDA approved drugs, 75 drug levels now list that myopathy is a potential side effect. This is quite big in numbers, so and we thought that this myopathy is very common and a very frequent adverse effect, and we have considered this in our discussion. Now, what is the data which will give us everything? So the data source is basically, you will find this available in the website. It's basically FDA data maintained by the FDA. This adverse event reporting system, FDA adverse event reporting system. The system is something like that. Whenever you are taking a drug or multiple drugs, if you come up with some side effect, the practitioner, medical practitioner, or the healthcare giver or the patient can report it to the FDA. And this spontaneous system is there that they will accept this, and they will with some demographic information, and they will put in their database. So the database is, as you can understand, it's quite huge, quite big, and the data is given in for each quarter. And we have taken the data from 2004 quarter 1 to 2009 quarter 4. So these are the time frame that we have chosen. For each quarter, this database has 3 different data sets. One on patient data, drug administrative info. One is particularly drug or biologic info, and the other one for the adverse effect. So this database is there, and anybody can look into the database and can download it. It is in ASCII file, or it is given in XML file also. So for each quarter, they have at most 300 to 400,000 patients information, or 6 to 8 million patients information. So in total, now we need to do some cleaning because we don't need all the information. So my objective is something different. So we try to create a new data set which concerns only with the side effect myopathy, and we use R for the first part to do this sort of filtering. But whenever we face this problem that when we are dealing with large data sets, with R is not found to be very suitable or very efficient. So what we did actually, we have to find the suitable drugs that were responsible for myopathy. Our general approach is that find the drugs which are most frequent among the myopathy patients. That is very naive approach that we have taken. And we just did some, okay. Oh, it is, yeah. So we made a cloud. And if you see, this is based on the frequencies that among the myopathy patients, which drugs are more common. But here we found some problem. For example, if you see that acetaminophen is the most frequent, which is the Indian version of paracetamol, the US version of paracetamol. So whenever people, this is quite safe drug, and you cannot say that this drug is causing myopathy. But this is the problem, that this acetaminophen is given for each and every individual. That's why in terms of frequency, it comes in the top. So it is there. But there are some hydrocodone or some statin drugs are there, which we find that they have some scientific reasons that these statin drugs may cause myopathy. So that is the problem, that the main disadvantage of this approach is that whenever I am taking this acetaminophen as the paracetamol basically, so it is very frequent. So we need some alternative way to discover the drugs, and for that we are using website which is called Cider. Cider, this website people usually use to define side effects. So this is quite commonly used and accepted website, and this contains information on the medications and their adverse effect. So we just consulted the Cider and we try to find which are the medicines which are in this list which are more frequent and causing side effects, as myopathy has side effects. So taking these two together, we filter out the important ones. So Cider is, I'll show you. Yeah. So whenever I go to the Cider and I just give a search myopathy, which are the drugs which has the common signal, this side effect as myopathy, and we found these are the drugs. So suppose there are 98 drugs which has the label that it may cause myopathy. Now we try to find out that which are the drugs which are most frequent among these 98 drugs among the data set we are dealing with. So we use some R packages to scrap this information, and we finally come up with 38 drugs that we found that they are more frequent. And secondly, among these 38 drugs, they have the recurrence in the Cider website also. So they are present in the Cider website as well as they are more frequent. So this is the basis from where I start my research. So now if I do the word cloud, now you see the most frequent is simvastatin. So that is a statin drug, and it has some scientific reasons why it is causing myopathy. Or you can have some tramadol or other drugs are also there. So now it is looking like more, I can relate it to the case of myopathy. So the new data set, after doing something, I will get something like this. So in the first column, they have the primary ID of the individual. Then we have the what are the drugs are given. For example, if you see the first two row, IDs are same. That means the first person is given two drugs. One is mifepristone, and the second one is misopro, something like this. And if you see the third row, it says the IDs are all same: third, fourth, fifth, sixth, seventh. So that means this individual is given, say, 1, 2, 3, 4, 5 drugs, and how the doses are there, when it started, when it end, and so all informations are there. We may not require all the informations, but for the timing, we have been able to find it out. And then we make a table like this, where the drugs, in the first column we have the drugs. First four, you will see that these are the single drugs. So we try to find how many patients are given this drug amiodarone. So amiodarone is given to how many people? Then chloroquine. Then what? The combination of two drug combination, 3 drug combination, 4 drug combination, 5 drug combinations. So we go up to 5 drug combinations, and we try to figure out from the data set that among this NIJ, how many of them are given this particular 5 drug. So 5 drug combinations. So in total, I'm getting some frequencies, and for each of these combinations. Now, it is to be noted that if you are having 38 drugs and you are taking 38, choose 5 combinations, the number is huge. So this finding was not being able to, we couldn't do it in R. So we try to do it in Python, and we get this thing, and then once again we come back to R. So this data set was huge. Okay. Now this is the study highlight. So what we want to do after having these numbers. So we want to study the drug-drug interaction study, and we are using 2 models. One is the binomial mixture model, and the other one is the approximation of this is a Gaussian mixture model. And for each of this mixture model, we are taking 2 competing models. One is, we call this fixed probability mixture drug count response model. The other one is count dependent probability mixture model. So we are repeating whatever we are doing for the binomial mixture for the Gaussian mixture. So this is just nothing but the approximation of the first method. So I will try to describe one method, and the rest will be just a simple approximation. So what we try to do. So this is the model. This is the statistical model. that let I indicates the number of drugs for I-way drug combinations. So it can be two-way drug combinations, it can be three-way, it can be four-way, it can be five-way. So we can have I-way drug combinations, and J is the jth I-way combinations. Nij is the total number of patients taking the jth I-way drug combination, and Yij is the number of cases among those Nij patients. So we are assuming this to be a mixture model, two component mixture model, and the mixing parameter pi into binomial Nij Yij pi dose, and 1 minus pi is, so why am I using two mixture model? The concept is something like that, that we are assuming that one probability of this will depend on the number of drugs we are taking. And we are also thinking that there are some cases where this number of drug combinations doesn't have any effect on this thing. So one is pi dose and one is pi fixed. Pi fixed means it is independent of the number of drug combinations, and pi dose means it is dependent on how many drug combinations are there. So this is the basic model that I have, that Yij be the outcome corresponding to the case population for the jth component in I-way drug interactions. And the first component corresponds to those drug combinations following dose response relationship curve. And the second one is the constant. We call this a fixed. Pi is the proportion of drug combinations that following the drug count response component. So this is the basic model I have. And for pi fixed, it's we have taken logistic regression. So it is e to the power beta 1 by over 1 plus e to the power beta 1. And for pi dose, it is e to the power beta 1 plus beta 2x over 1 plus e to the power beta 1 plus beta 2x. So when x is the number of dose you have, so if x is equals to 0, then these two models becomes identical. And once we have the model, we can find the parameters using, for the mixture model, that is quite obvious that we'll be using EM algorithm, and it's not something very delicate or very extraordinary thing that we did. It's just we use the EM algorithm. So I don't think I will waste my time to discuss how we have done this. So this is the basic model, and this is the likelihood, and we all know that how to find the parameters using EM model. So we have used EM algorithm to find the parameters using the E step. This is the E step. This is quite straightforward for the logistic mixture, and this is the M step that usually we do. Okay, I will just describe the method more. So the whole process we just try to figure out in a flow chart. So first we initialize the parameter. In the E step we use the conditional expectation, and the M step we calculate pi, and we obtain beta 1 beta 2 from these Wij's, and we repeat this till the convergence is achieved. Okay, so this was the first when we use this fixed thing. And in the second model we call this as count dependent probability mixture model. So the difference is not, earlier it was beta, if you see the probability, it was beta to x, now it is beta to xi. So we believe that where pi I is the proportion of I-way drug combinations that follow the drug count response component. Earlier it was just pi, now it is pi I. So we call this as count dependent probability mixture drug count response model. And the rest is just the same. So we did the E step as well as the M step. And we perform a likelihood ratio test where the null hypothesis was that all the pi i's are same against the alternative, and we reject the null hypothesis whenever d is greater than chi-square into k. So this is the standard, and for this the degrees of freedom is found to be 4. Whenever you have the frequencies to be large, we can approximate using this model by a Gaussian regression model, so that it becomes much easier. So it's a one-step problem that we just use De Moivre's approximation, where this likelihood, we approximated the likelihood using this, and this becomes a Gaussian regression model, mixture of Gaussian mixture model, and the computation becomes much more easier. The steps are almost same. Now, once we have the estimates, now we are in a position to find the false discovery rate, and on the basis of this false discovery rate, we want to rank the risk of all these drug combinations, and we try to find the drug combinations which are potentially more dangerous in terms of side effects. So what we did actually, this is whenever I'm doing using a mixture model, then the FDR becomes a byproduct of the estimation process. So FDR is defined as 1 minus pi into f naught y over fy. This is the probability of combinations follows fixed curve relationship given y less than equals to y. So for this, we are using the LFDR, the concept given by Efren. And for each and every drug combination, we try to find this, this FDR and we rank them. So this is the result that we can put them side by side. So this is the thing that for the fixed this mixture model, it is pi1 is 0.12, whereas for the count it is 0.08. And whenever I'm doing this for the normal model, the results are a bit different. But the pi2, pi3, pi4, pi5, these things are there. So I have taken up to 5 combinations. So that's why whenever I'm talking about count dependent, so that means it depends, pi i's are different, and the regression parameters are also there. Beta 1, which is minus 1.79 for the first model, for the second model is minus 2.2, and for the approximate normal model, though not very close but not very way either. So the results are more or less consistent, that can be seen from these two models. And we did compute the log likelihood, AIC, and residual sum of squares to check the goodness of fit. Now, once we have this thing, this is the salient features of that we see that log likelihood is maximum for the Gaussian mixture CDRM. The RSS is pretty much same for all the models. And from the AIC values, it is clear that both binomial and Gaussian mixture model, CDRM, this is count based basically, performs well than the fixed mixed model. Now, once we have all this parameter estimate, we try to plot the count dependent risk and the risk curves for different models. So what in the x-axis, we have the drug combinations, 1 drug combination, 2 drug combination, 3 drug combination, 4 and 5. And in the y-axis, we have the proportion of patients, and we just try to plot the fits. The red one is the just opposite. The legend is completely wrong. The red one is the varying risk, and the green one is the constant risk. So this is for the fixed model. But whenever it changes to CDRM, is the count dependent. The curve is almost similar, but you can see that it's much more steeper compared to that one. And once again, the red one is the varying risk, and the green one is the constant risk. So it can be seen that whenever I have more drug combinations, the frequency, the proportion of patients, if you see that the risk is increasing. So that is quite not logical, and we can defend this, that as number of drug combination increases, there are chances of much more complications which may result in side effect like myopathy. We did the same for the Gaussian approximate model, and we got similar sort of results. And this is the main most important tables that we have come up with, that for each of these two drug combinations, for example, we have simvastatin as a statin drug with tramadol. So if this combination, if you see the frequencies, it's 0.6028, and if you see the minus log LFDR, it's 158. So we try to rank them in order of this FDR, and for each of these drug combinations, we computed this. So for the first few, this is once again simvastatin is involved. So whenever simvastatin is given with some other drugs, the FDR is it comes top of the rank. And whenever I'm taking a 3 drug combinations, for example, it's not working. I'm sorry. So for this, we from 2 drug combinations to working. We computed the same for the three drug combinations. We computed this for the 4 drug combinations, and we computed this for the 5 drug combinations. And for all these drug combinations, we tried to find out or we try to rank them according to the risk. And this is the main finding of this whole analysis, is that we can say that whether a particular drug combinations, let it be 4 drug combinations or 5 drug combinations, among these 4 or 5 drug combinations, which are more lethal in terms of side effects. But here one thing we must acknowledge, or we must say that the limitation is that we all know that if there are multiple drugs, say A, B, C, so whenever A is given prior to B or A is given after B, has serious implications. So this thing we didn't consider in this work. In a separate work where we used some sort of graphic mining method to find this the direction that in which the drugs are given. So I don't know whether my machine hanged or not. Okay, so I'm so sorry because I couldn't show you the last slide. I'm almost done. The thing is that we tried to do this for this sort of drug combination, say up to 5 drug combinations. But once again, yeah, it is coming. So this is for the 3 drug combinations. We have this. Then we have this 4 drug combinations. Okay. I'll come to this. So in this work, we compared several methods on the mixture model setup. It is found that all models except fixed count based models perform really well. This is all what we got. The direction of drug administration has not been considered. A graph theory approach has been adopted to consider this analysis. We have taken binomial mixture. We can take more stable thing which can take care of the variation using a beta binomial mixture. We have not done this yet. And we wish to work in this area once again, but handling the data is becoming more and more problematic. And these are the few references. And this is one paper in the second reference. I did some work where we did some graphic mining of higher order drug interactions and their directional effects on myopathy using this record. So with this, I think I'm done. Thank you.
Okay, thank you, Varindamda. That's a really nice and interesting talk. So while I don't see any questions so far in the chat box, so I request the participants to write if they have. But I have a couple of questions, so just I'll take maybe 1 or 2 minutes just to understand it better. So I think, see the disease that you are specifying here, what is the name again?
Myopathy.
Myopathy. So what I was wondering, because since you have a vast amount of data available, you are just using a mixture model kind of thing. Is it really appropriate to just classify that into 2 different parts like dose and fixed? Because it might happen that, see, there might be a cluster kind of thing in the population depending on the age, gender, and different kinds of background. So a finite mixture model where we don't know actually the number of components and the models will automatically pick that up, that would be more appropriate. That's what my thinking is. What do you believe?
Okay, Kiran, I completely agree with you. The thing, the do in pharmacokinetics or pharmacodynamics, whenever they are doing this sort of a pharmacovigilance type of thing, they usually follow that. They usually say that the drug combination will follow either of these 2 approaches. That either it will be fixed or it will be varying. But whenever I am talking about, as you mentioned, that it may depend on the age, it may depend on the ethnicity, it may depend on some other things are also. So yeah, introducing or introducing more and more component to the mixture model may give better idea. That's completely, because whenever I am talking about fixed and the varying, that means I'm assuming that for the varying, the individuals, they are homogeneous. So we are not considering the inherent heterogeneity there. So if you consider the age and other parameters, additional parameters, that may give better idea. Yeah, I completely agree with you.
And I see another question here. So the question says, is this study done only on one side effect, myopathy? Can we extend it for the other side effects?
The first answer is yes. It has only we did this for myopathy, and we can do this for other or we can combination of side effects. But as you can understand that when if I'm taking two side effects together, then the data set, the size of the data set will get increased, and these complications are here the theory is not a big problem. The problem is the computation. Suppose for this you have 75,000 case and around 3 lakhs control population. So for each of this huge data set, you have to find how many 5 drug combinations are there. So how many 4 drug combinations are there. So whenever I'm taking one disease at a time, then the data set becomes much more segregated. But whenever I'm taking two diseases together, it is doable, definitely doable, but the computation complexity will be much higher.
Okay, I think that is understandable. So thank you, Arindam again for your nice talk, and we still might have some more questions, so that we'll have in the end. Okay.
Sure.
Okay. So now I'll request Dr. Kiranmoy Chatterjee. So Kiranmoy, it's yours.
Yes, okay. May I start?
You have to share your screen.
Yes. Can I see my slide?
Yeah.
Yeah. Okay. Good afternoon to all. At first, I'd like to thank Kiran and Diganta sir to invite in this young statistician meet. Today, mainly I will talk about my primary research area, what is it's called population size estimation based on incomplete multiple system. That means when you have different sources of data, but all are incomplete, then how will you estimate the true population size? So this is actually a joint work with Dr. Pujamitra Bhuya, who is currently in the Imperial College London, and I'm working in this field since my PhD tenure. So, okay, let's start. So, what's the basic problem is that means suppose you want to count any population, a population with some features like number of drug addicted individuals in a town, or say maybe number of people who are affected in a very serious natural calamities, or maybe war, anything, or maybe somehow you want to calculate the figure of how many child labor are working in a particular city, or even in a whole country. Okay, so each of these kind of problems, you don't get the actual data because you cannot count all, because most of these events are very much hard to count. Okay, so then the problem is how to estimate this problem, how to estimate this population size, because this kind of problem, this kind of estimates we often require, we mean mainly by the federal government, state government or central government, whoever it is, but they need this kind of data for some policy formulation. So actual data or actual count, we always require the actual counts. Otherwise, the whole thing will be messed up. So my area of research actually lies in this domain. So this kind of the basic technique, what is used in this problem, the technique is very well known. That is called capture-recapture method, which is very famous to estimate for wildlife population. But for human population, things are not exactly same with wildlife population. So for human population, we call it multiple system, which is equivalent to the capture-recapture method. But technically, in some sense, it is different. So here I am presenting that there are various kinds of applications of this kind of problem. And also another kind of problem which is very traditional, that to estimate the undercount, because when a government of any country performs the whole census operation, so we know always that if the population is very large, then it is not possible to count exact figure. So every developing country tries to estimate the undercount or maybe the overcount. Overcount is very hardly found, but grossly it is undercount. So they try to estimate how many people are, what is the rate of undercount in the census. So our country, India also do this stuff, but very few of us know about this matter because the result they publish, but it is not highlighted too much because the estimate is not finally adjusted to the actual count. And it is also it is done in US also. They have a long debate since 1980, but they are doing very sophisticated statistical tools they are using to nowadays to estimate the undercount. But still, final result they don't adjust with the actual count. So they separately publish the result of undercount like India also. So if you just give a figure, if you just see this figure in 2011, also in India, 23 people out per 1,000 people, around 23 people are undercounted, or you can say omitted. So it gives you nearly 3 crores within India. And if it is in the central zone, it is highest undercounted. So around 41.67 people per 1,000 people who are counted, around 41 people are missing. So this sometimes gives you a very large count who are actually missing. Now, this is not the aim, because the main question is that what the method they use to estimate this figure, that method itself is under question. Okay, so people experts think that method usually underestimate the population. So that means actual figure may be larger than this. So, okay, just now come to what is the problem basically what is the problem. If you see this figure clearly, then suppose this rectangle is your area, this is the population, and in the people in this area you have to count. So you have two lists, suppose list 1 and list 2. That means list 1 made by some agency and list 2 made by some agency who are supposed to be independent. So obviously there may be some people who are counted by both the lists, and there may be some people who are counted who didn't count by any of the lists. So these people actually unknown to us, because the people lies in the union of two sets. These are of the counts. So the remaining people are actually the unobserved counts, which makes the total population size unknown. So if you classify these two attempts in list 1 and list 2 with respect to their presence or absence, in means present, out means absent, then we can classify the data in a 2 contingency table, right? But the fourth cell is unknown. So it is actually the incomplete contingency table. So that unknown cell makes the population size unknown. So our problem lies mainly to estimate this or equivalent to estimate the capital N. So some basic method which assume to this kind of data, because here the data is quite different. It is not the conventional statistical data type, and also it is not the exactly discrete data analysis in a continuity table. So it has extra one feature that the one cell is unknown. So you can see it as a missing data problem also. You can see it in other way also. So the basic problem actually to estimate the N, and to estimate the N, what we need basically that if you assume the population is closed population means there is no birth or death between these two captures. Okay, list 1 and list 2, and population also homogeneous in nature with respect to their capture probability. So then, if you see that model actually consists 4 parameters, including N and the other 3 cell probability, like P11, P10, and P01. This P01, P11, and P10. So total 4 parameters, but you have only 3 data. Okay, these blue cells are known only. So obviously you require one in assumption. So basically 2 lists are assumed to be independent. This is the basic method. Okay, and if you assume this, then you will get the estimate that the x1 dot into x dot 1 by x11. x1 dot and x dot 1 are the marginal form of list 1 and list 2. Okay, so this is the basic estimate. It is used popularly in various domains in epidemiology and other there is many kind of application in social science. But experts think, and it can be proved also, that these estimates have a serious problem of bias. Bias mainly due to the independent assumption, because in reality these assumptions in almost all the cases won't work. Okay, so what to do? You can enter some dependence parameters in the model, dependence between the 2 lists, list 1 and list 2. And by including some dependence parameter, there is another method, a model called MTB model. I will not say about this model extensively. I will go to our model directly. But here in MTB model there is a dependence parameter. But this model also has a problem in dual record system. Dual record system means when I have only 2 sources of data, 2 lists. So this model suffers from estimability problem, and also the parameters are not identifiable here. So that's why people always recommend to use an extra source. So together there is 3 sources. So if you have 3 sources, then you have some good working model, but in the 3 sources, you can think of the extension of this picture. Still, there is some people left who are not counted by any of the list. So the problem lies in the same way that in the last cell, these blue cells are known. Okay. So it is like a 2-cube table, 2-cube continuity table, in which the last cell x dot is unknown. So there are some existing models like log linear models, and I have also told the MTB model. But in MTB model, the assumption to make the model working, to make the model to make the parameter estimable, what assumptions they have taken, that assumption also sometimes not valid. And in log-linear, there are some log-linear models. Obviously, here also you have to take some assumptions like three-factor interaction. Three-factor interaction means since there is three lists, three sources. So to work this model, we have to assume that there is no three-way interaction or joint interaction of the three sources. So there are some two existing models depending on two different assumptions. Okay, these assumptions mean the dependence between first list and third list is nil. So this is also sometimes not valid. Okay. So, and another problem in the existing model MTB that what the way they collect the data and they have developed the model MTB, they have only the 5 sufficient statistics. If we consider the model in the TRS setup, that means triple record system setup, then we have only the 5 sufficient statistics. The problem is that though if I represent this TRS data in this fashion, in the 2-cube table fashion, I have 7 sufficient statistics. But according to MTB model, their data structure is, the way of capturing the data is different. That's why they only have the 5 data. And we think that they also don't use the full information what can be available from a TRS system, triple record system. So what we did that we proposed a completely new model so that our main aim was to develop a model that is as simple as possible to give the estimate, because this kind of problem, this kind of scenario is often experienced by official statistics, and this is done by government or any government sector office. So our primary thought was to give a simple method, and what we did that we take a triplet like Y, Z, and H, where Y, Z, H represent the list 1, list 2, and list 3 inclusion status of an individual H. Suppose individual is marked by H individual. So for an individual, Y, Z, and W denotes his or her status in the 3 lists respectively. And what we model this triplet, to model this triplet, we invoke 3 latent variables like x1, x2, x3, which are basically a Bernoulli variable independently, so that this structure gives you the whole exact scenario of a population. Suppose I have a population with some 100 people. So maybe there are 20 people who are independent of their inclusion status in the 3 list. That means there is no dependency between the inclusion in list 2 and list 3 with respect to list 1. Okay, for those people. Okay, so suppose the 20 people means 20% people. So I mark this as a alpha 1 proportion people who have, here alpha 1 proportion people have a dependence between list 1 and list 2. That means if he is captured in list 1, then obviously he will capture in list 2. Okay, so there is a direct positive dependence. Similarly, there are alpha 2 proportion of people in the population who are actually their dependence between list 2 and list 3. That means if he is captured in list 2, then that means automatically he will capture, in list 3. Okay, so this is a positive dependence. So in this way, there are some people who have a dependence between list 1 and list 3. That's why here list 1 and list 3 are same value, same variable. Okay. So, and the alpha 4 means this alpha 4 gives you the joint interaction. That means if he captured in the list 1, he will capture in list 2 and list 3. If he not captured in list 1, then he will not capture in list 2 and list 3. So this is a positive dependent, what we model. And the remaining, that means 1 minus sum over this alpha I, this is called 1 minus alpha. So for remaining people, for remaining individuals, they are independent. Their capture status are independent. So this model is a very simple model, and this model gives you a whole exact scenario of your population, of the population of our interest. So this is the main thing of this work. What this work has been already been done and it has been published, but then we will talk about its extension. So, but here similarly, here since total number of parameters becomes 8, it is just one more than your sufficient data. So that's why I require one assumption like alpha 3 equals to 0 or alpha 4 equals to 0. That means in some population, like before that, I can assume that there is no 3 factor interaction, or there is no interaction between first and third list. And the resulting MLE will be simple. You can simply estimate, you can simply find the MLE. We have applied the data, we have applied the model in the data of malaria incident in Netherlands. So this is the data of malaria incident, and this is the 7 cell. This is the 7 cell. And the sum of this is the total observed count. And another data from urban blackness census count from USA in 1990. So this is another TRS data. And we have found that we have analyzed the data with comparison to log linear model and MTB model. And we found that our model have better fit the data according to AIC. And also it has very tight confidence interval with respect to others. Also sometimes LM2 performs good, but with respect to fit with the data, our model performs well. And in urban black people data, and here also our two models, TBM1 and TBM2, perform better than the existing model. And we have also performed extensive simulation study. Here I have given some of them. Here also we have found these models, our models TBM1 and TBM2 have better relative MAC for both small population and quite large population in this domain. And what is the advantage of this model is that here all the parameters of this model are well interpretable. Every parameter have clear interpretation. And it was a lack in the other model, and this model can be extended to a negative to capture negative dependency. Here I have extended with positive dependency. You can redefine this as a negative dependency, and also there is no problem of identifiability what was in the MTB model, and that this model now this work already has been published in JRSFA, and now we are actually working on the extension of this model including the heterogeneity. So heterogeneity is individual heterogeneity. So to input the heterogeneity, actually we require the model, the main structure is quite same, but here I have included the H. H means H represents the heterogeneity. So where each and every LH is a Bernoulli random variable who are independent for L over L, and to model the heterogeneity, we have taken the logic model on P. P means the capture probability of HF individual in the LH list. So this is the model, logic model in terms of a random effect and the fixed effect. Fixed effect in terms of source variation is L runs from 1 to 3, source or list you can take, and random effects are R. So together we can take it as a B, because we can assume a random distribution on B itself. So what we did is that, and the main problem is that, hello.
Kiran, just 1 minute. So can you please wrap it up in next 2 or 3 minutes?
Yeah. 1 to 2 minutes. So the main features of this model that when you input heterogeneity, your model will automatically be very complex, and that's why most of the people will do a very sophisticated computation of Bayesian analysis and also some mixture model and everything. But here, what we actually did is that the complexity actually lies in when you model this data, your data, the cells can be modeled in a multinomial fashion. Okay, but with the cell probability Pijk, and the problem is that this Pijk the resulting likelihood will be mathematically intractable due to additive structure of the cell probability. Okay, so we did like this. I have given one example like this. So what we did that we have invoked the idea of data augmentation, and we introduced some. We have partitioned that each and every cell with respect to how many components is in the probability, and we introduce a new latent variable y, so that our model, our likelihood will become easier to handle. Okay, and then we formally just use non-informative pairs of all the underlying parameters, and since we have got the explicit form of closed form of conditional posterior, so we can go with gift sampling, and we did it primarily. It is under working out here. We are working on this problem. So just till now we have applied the method intimate partner violence data, and we found it is primary result. We found our model work good, where the other models actually when you input heterogeneity, most of the existing models in this domain are giving a very distorted kind of result. So every model gives very scattered results. So there are various reasons. I will not talk about that. Yeah. So we have performed a extensive simulation study, and here also we are giving this, and we have our models have a very good coverage probability, and also the bounds are tight here. So we have studied the simulation with population size 200 and also population size 500. So these first two our proposed model, and remaining the existing model. So that's it. So it is actually we are working on this problem. So we are almost done. Let's see what we can do. And these are some references. And then thank you to all.
Okay, so thank you, Kiranmoy. I don't see any questions in the chat box now. but just wait few more seconds, and if not, then I'll request the participants to write their questions in the chat box, and we just keep it for the end discussion. Okay. So now I request Jayabroto for his presentation. So Jayabroto, good time.
Yes, sir. Is it visible?
Yes, yes.
Okay. First of all, I would like to thanks to the organizing committee of YSM for giving me this opportunity to present here. So this is the I'm going to present one of my PhD work, a semi-parametric quantile regression approach to longitudinal outcome with zero inflation and incompleteness. This is a joint work with my PhD supervisor, Dr. Kiran Das. The outline of the talk is this, given as follows. First of all, I will give an introduction where I describe some few basic terms and also describe the data. So how the data works here and how the data looks like. And then I will describe the model and methods. Then we discuss our constructive model with compare with some other models by checking simulation studies, and then finally analyze the HRS data, and then end the talk with some discussion. So here are some few basic terms. What is longitudinal data? A data set is called longitudinal if it tracks the same type of information on same subjects at multiple time points. This is basically mixture of cross-sectional and time series data. And the second part, we called a variable as semi-continuous. It means that the distribution of the variable is continuous, except it has a probability mass at the point 0. This kind of distribution or this kind of variable is commonly known in the literature as a zero inflated variable, and this kind of distribution is generally known as zero inflated distribution. Now, in longitudinal data, there exist two kinds of missingness. One of them is monotone missingness, and another one is intermittent missingness. By monotone missingness, I mean if a subject is missing at time point t, then it will be missing the remaining time point also. And the intermittent missingness, we mean that the missingness is not monotone. By that, I mean that the pattern of the missingness is haphazard. That is, if a subject is missing at the second time point, and then it may again appear at the third time point, and again disappear at the fourth time point, and so on. This kind of missingness is known as intermittent missingness. So here we propose a Bayesian approach for modeling this incomplete zero inflated longitudinal response. So before I going to jump into the model section and the data analysis part, I will give a quick recap about the quantile regression part. So what is regression? It is basically a summary of the relationship between response variable y and a set of covariate x. And generally we are using least square regression, which captures the mean of y, how the mean of y changes with different values of x's. And sometimes a single mean curve is not informative enough. Because of that, we need quantile functions to get a more complete view of the data. For this, suppose we have an example here that our response is a birth weight of a children, and the covariates are mother's age, marital status, and education. Now we are interested in knowing the factor which influencing the birth weight, influencing the lower birth weight of a child, because lower birth weight is known as several health problems of a child. So we wanted to know what are the factors which influencing that lower birth weight. And in this situation, analyzing the data by mean regression will not give any satisfactory result. For that, we need to go beyond the mean regression. That's why quantile regression play a key role here. So what is called quantile regression? How it is work? Quantile regression models the responses at different quantile levels. It helps to get an idea about the complete shape of the response distribution. Objective function of quantile regression varies over different levels of quantiles, leading potentially distinct solution, which can be interpreted as an effect of covariate changes over different level of quantiles, different level of responses. And the third point is the main point, why we are using quantile regression, because it is robust in the sense that it do not need, it do not require any distributional assumptions here. So here is how the quantile regression looks like. Basically, Coenker and Bassett initially proposed the quantile regression in 1978. Suppose we have a data in the form that xi transpose yi, I runs from 1 to n, in group of data. Y is the continuous response, which we called as a response, and fy is the, we called fy is a cumulative distribution function on CDF of the response variable, and xi transpose is the p-dimensional row vector of the regressors. Then the quantile the equation looks like this, where tau belongs to 0 to 1, exclude the case of 0 and 1, and q of I basically gives the inverse cumulative function of the response variable, which is defined in this following way. And beta tau is a quantile specific vector of parameters for the tauth quantile. Alternatively, one can write down the following linear model yi, linear model in this following form, that y is equal to xi transpose beta tau plus epsilon I, where the residuals epsilon i's are IID with the tauth quantile is equal to 0. Remember one thing, that the distribution of epsilon I is not known. You just assume that they are IID. That is the main point of using quantile regression here. So how do we estimate this beta tau here? Coenker and Bassett come up with the fact that the objective function to optimize the beta tau is this given here, and Coenker and Bassett developed simplex algorithm to solve this beta tau, where Gerasi and Botta in 2007 show that asymmetric Laplace distribution also can be used to achieve the same goal here. But remember that for a single given tau, the beta tau is different for each tau. So for each tau, we have to calculate this beta tau, so on. And that is the basic idea of quantile regression here. Now here comes the motivation part, or the data, what kind of data we are going to use here and how do we analyze it. So we analyze the data from the health and retirement study conducted by the University of Michigan for an aging population. The study started in 1992 with 1929 subjects. Those are aged 50 or above, and ended in 2008 with a follow-up frequency of 2 years, which we refer as waves throughout our study. So out of 1929 subjects, only 1 to 2 subjects have complete information, and that's why I already told that our data set contain missing values, and there are, so you see that only 1 to 7 subjects have missing values observed. So the rest of them, they have 2 type of missingness. Most of the missingness pattern of the data is monotone. Our covariate set contains calendar age, body mass index, indicator of different insurance status, different disease status, total monthly income, total asset, and total debt. And what is our response? Our response, we took out-of-pocket medical expenditure as our response variable. What is out-of-pocket medical expenditure? It is the cost related to the medical services like doctor's visit, hospital visit, drugs, etc., but excludes the cost reimbursed or paid through health insurance. Out-of-pocket medical expenditure is treated as an important source of financial risk. Details are given in their paper, Mukherjee et al. It reflects the financial status of a person as well as physical status also. So for an individual, if no medical expenditure, or if all the medical costs are paid by their respective health insurance company at a particular way, then for that individual, their out-of-pocket medical expenditure will be 0. And hence our data set contain excess 0. That's why it is a zero inflated or semi-continuous data called at the beginning. Here is the model description. We use a 2-part model proposed by Duan and al. in 1983 for analysis purpose. The first part of the model, we consider a dynamic probit model for modeling the probability of 0 or non-zero responses. And in the second part, we consider a dynamic joint quantile regression model for modeling the non-zero outcomes. And as I mentioned, that our data set contain missing values. So In this work, we also consider missingness only in the longitudinal response. So we consider a multinomial probic model for modeling the different type of missingness. So basically there are 3 type of models here. These 3 models, dynamic models, are connected through a random effects, and they are independent condition on the random effects. So before going to the proposed model, here are some few basic terms that we consider zero inflated longitudinal response measured from n different subjects at t different time points, and the set of covariate contains j covariates which have time varying effects. By time varying effects, I mean the effect of the covariate varying over time, and the j prime number of covariates have time invariant effects. Yit is response from the ith subject at the tth time point, and ytl denotes the non-zero response from the ith subject at 11th time point. So here the zero response model, form of the zero response model. Here we define EIT as a random variable which is related to YIT in this following way, that EIT takes 1 when YIT takes positive value, or EIT takes 0 when YIT is 0. So clearly PIT indicate the boundary random variable with success probability, and we introduce a latent random variable RIT, which is related to EIT as follows, that EIT takes 1 when RIT positive and EIT takes 0 when RIT takes negative or 0 values. We model RIT in this following way, given that in this equation, where the first part, this set of the parameters of xijt is a function of t, because xijt is a time varying effects, and this is the set of covariates which have time varying effects. That's why their parameter is fixed throughout the time. BI is the subject specific random effect, capture the longitudinal dependence between RIT and RIT prime, and EIT is the error distribution, which follows normal 0, 1 in this case. And using one that is this model, come up with the fact that model PIT in this following way, where capital phi is the distribution function of the standard normal distribution, and we model alpha jt, that is this, as a polynomial function in this following way, given in the equation 3, where the optimal degree of the polynomial is obtained by their respective information criteria like AIC, BIC, etc. For the zero response model, we use the following Tawith quantile regression. For the Tawith quantile regression, we use this model, where this part is called the intercept of the model, and this is the set of the covariates, effect of the set of the covariates, which is varying throughout the time. That's why their coefficient is function of t, whereas these are set of the covariates which is non-time non-varying effect, and that's why their coefficient is fixed throughout the time. Ci is the subject specific random effect, captures the longitudinal dependence between 2 non-zero responses for the Tawith quantile specifically. Now for a fixed tau, those time varying effects beta tau j, that is this, is modeled as a polynomial function of t, where the optimal degree of the polynomial also can be obtained by the respective information criteria AIC, BIC, etc. Now what is the distribution here? So first we pre-specify the set of taus, name is set tau 1, tau 2, tau k, and then the density function, this is basically data driven density or pool density, the joint quantile density, which initially proposed by Jiang and Wang in 2015. This looks like this, where the first part and the last part of the density is indicate the tail, and where the intermediate part basically gives an uniform distribution throughout this uniform probability throughout this region, where the theta and theta, this kind of thing, the previous model, theta and theta are the parameters related to the left and the right tail of the distribution, which is modeled as a by the tail of a generalized Pareto distribution. Why generalized Pareto? And this model is also known as linearly interpolated generalized Pareto distribution, or LIGPD, as proposed by Jiang and Wang. And Jiang and Wang took several distribution to fit the tail distribution, and they come up with the fact that generalized Pareto distribution gives the more robust result comparatively to the others, and that's why they took generalized Pareto, and we directly took it as it is formed. Now the subject specific random effects BI and CI are correlated, and their joint distribution looks like this. So in this way, the zero response model and the non-zero response model are correlated through this BI-CI correlation thing. And the third part here, the model, we jointly model the probability of missingness. So to do that, we first introduce a random variable SIT, which indicate whether a subject is intermittent missing or monotone missing or observed at tth time point. Here how they are related, that SIT takes 1 if the subject I drops out at measurement T, that means it is a indication of monotone missingness, or SIT takes 2 indication of intermittent missingness, and SIT takes 3 indication of observed values. Now we define a latent random variable, random vector, not variable, which takes 3 different values, which have 3 different components, and they are related to SIT in this following way, that SIT take 1 if this maximum value is ZIT1, SIT takes 2 if maximum this is ZIT2, and maxi 3 if maximum ZIT1 is ZIT3. So therefore, this is the probability of indicating whether a subject is missing. By missing, I mean monotone missing or intermittent missing or observed at tth time point. So now we model ZITK in this following way, given in equation 7. Here BI is same as described in equation 1, that is the zero response part of the model. And DIT basically captures the dependency of ZITK and ZITK prime. Epsilon ITK is the error, and their distribution is given as follows. And we link the missing data process with the longitudinal outcome process by assuming that they share the same random effects BI. By sharing the random effects BI with the longitudinal outcome process, the missing data model accounts the non-ignorable missingness. That is the main point here, because BI is basically same as described in equation 1. So in this way, the non-zero response model and this probability of missingness model is related, and the non-zero response model and zero response model are missingness throughout the their joint distribution. And that's why in this way we link these 3 models together. And here comes the joint likelihood part. Here we define θ1 denote the set of all parameters from the non-zero probability model, and θ2 denote the set of all parameters from the quantile regression part of the model, and θ3 denote the set of all parameters coming from the missingness part of the model. So these 3 models are related throughout their random effects and share the parameters and so on. So here comes the joint likelihood. Here the first part, this part basically indicate captures the model related to the zero response part. This part captures a model related to the non-zero response quantile regression part, and this part coming from the probability of missingness part of the model. So multinomial probit model, that is the thing. Here delta IT basically this indicator variable, and FZIT we don't have space here, so we write this FZIT model in this form. Here FRIT is density of this thing, and FRIT is same as described in equation 5, that is basically this density is basically the pooled density, joint quantile density proposed by Zhang and Wang, which is known as linearly interpolated generalized Pareto distribution, and the remaining density is as given in the previous section. So how do we estimate those parameters? So it is very difficult from the joint likelihood to get an estimate of those parameters by the maximizing the above likelihood using classical regression approach. So we use Bayesian approach to obtain those parameters. We took a prior distribution for the parameters and calculate the full conditional distribution, estimate the parameters using MCMC, and we use hybrid combination of Gibbs and Metropolis algorithm to run the MCMC until it's converged. And this is the general form of if pi alpha, pi eta, these are the basically prior distribution, and we multiply this to the likelihood to get the posterior distribution, and then we calculate their posterior mean to achieve to say that that is the estimate value of the parameters. Here comes the simulation part. First, we generate RIT values from the given model, and once we generate all the RIT values, then we check whether the RIT takes positive or negative values. If the RIT is negative, then we define EIT as 0, and if the RIT takes positive value, then we define EIT as 1. if EIT takes 1 values, then we come to the next part, and here we define YITIL, and for those EIT values which takes 1, we replace this EIT as the YITL values from this model. And once the zero inflated non-Gaussian, that's why in this way we generate a zero inflated data, longitudinal data here. So once the zero inflated non-Gaussian longitudinal response are generated, we compare their performance with the conventional quantile regression as proposed by Cohen and Bassett in 1978, a Bayesian quantile regression approach for the longitudinal outcomes using asymmetric Laplace distribution as proposed by Girashi and Bottai, joint quantile regression approach as proposed by Jiang and Wang, and our proposed approach. So here comes the plot, the result. Here we see that this is basically indicate the MSE, different quantile levels, the value of the MSE. And here we see that the solid line indicate our proposed approach. This line indicate the MSE for Jiang and Wang's proposed approach. And this is for the Girashi and Bottai's approach, that is asymmetric Laplace distribution, and this is the traditional quantile regression approach. So this is for beta naught, beta 1, and beta 2, and we see that in all the scenario, our model gives better performance because our model gives lower MSE comparatively to the others. And in all these cases, we see that traditional quantile regression, which is initially proposed by Cohen and Bassett, gives relatively higher mean square error. So this is for n equal to 100 sample size, and this results for n equal to 200. Here we also see that the MSE is quite low relative to the others for each of the parameters. And this is for n equal to 500. Here you also see the same result, that our model gives better performance relatively to the others. So this is the one part. And the next simulation study, the first part, we do not incorporate missingness in our model, and the second part, we incorporate missingness in our data. We have 80% complete data and create 10% monotone missingness and 10% intermittent missingness. So we took the same parameters as in simulation 1, but now we analyze the complete data, that is the data has no missing values. Then estimate the model parameters value at tau at 0.1, 0.5, and 0.8. Next, we consider the data with missing values, but do not model the missingness. The model parameters are estimated at the same quantile levels, that is tau equal to 0.1, 0.5, and 0.8. And at the third part, we use our proposed approach and model the missingness using the multinomial probability regression model and estimate the model parameters and see how it is work. So when we took the residual distribution as normal 0, 1, we see that complete data, and this is credible interval, length of the credible interval. This is the coverage probability, and we see that the biases for the complete data is always low. Where if we do not do not model the missingness, then its bias is relatively high. Comparatively, when we model the missingness, bias is relatively low. This is for residual distribution normal 0, 1. The same results hold for residual distribution when we took T3 as a residual distribution. For the same parameter, and of course complete data always give you better performance rather than missing observation. So that's why complete data always gives lower bias compared to the others. But our main goal is to check if we do not model the missingness, then, and if we model the missingness, then what happens. Then we see that also the here bias is also high. The bias is pretty much low comparatively to the when we do not model the missingness here, when residual distribution is T3, and when residual distribution is chi-square 1. In that case, we also see that our model gives better performance when we do not model the missingness here. This again justify to use that kind of model here. Now here comes the HRS data analysis part. We fit the above model in our HRS data where the response is out-of-pocket medical expenditure. I've already told at the beginning of this presentation. Now, for both monotone and intermittent missingness, the ith subject is missing at wave t, then the following model ZITK consider the latest available covariate values. Now, for estimating the model parameters based on the joint likelihood, we employ Markov chain Monte Carlo method. The starting values of the model parameters are generated from their respective prior distributions. And we run the chain 10,000 times and discard first 2,000 iterations as a burn-in. and we estimate the model parameters by their respective sample means. In this way, we estimate the model parameters, and we see the outcome here. These are the two effect that I mean the effect of the time varying effect, coefficient of the time varying effects for the zero response model. Here we see that there are 4 insurances: other insurance, no insurance, employment insurance, where the effect of the government insurance for the non-zero probability response is pretty much good, because it see that there is an increasing trend after wave 5. So it indicates that government insurance government insurance is benefited for the older people. And here we see that how the probability of zero response effect of the total income, total number of hospital stays, and total deaths effect for the probability of zero responses. These are the non-zero response part of the model. Sorry, the zero response part of the model, and this is coming from the non-zero response part of the model. Here we see that we plot those effects at different level of quantiles: tau 0.25, tau 0.5, and tau 0.75. And we, when we see the picture, we keep in mind that the lower quantile indicate the financially weak but physically sound group of people, where the higher quantile indicate the financially sound but physically weak group of people. So this is the picture for when tau is 0.25. This is a picture when tau is 0.5, and this is a picture when tau is 0.75. We see that they are not the same, and they not reflect the similar result. So in 0.75, we see the number of hospital stays, total income, total death, orally increasing, whereas the total depth is not increasing. It is pretty much fixed for the time, and so on. So, and again, for the time non-time varying effects coefficient, here we see that the education level has an impact over the non-zero responses for the tau equal to 0.25 quantile, and for tau is equal to 0.75 quantile, where gender is effective for tau 75 quantile. Cancer, heart problem, and stroke, they are all effective throughout the all quantile levels. So this thing again indicate why we use quantile regression over ordinary regression, because in ordinary regression we do not see that kind of thing. And here is a discussion that in this work we propose a linear mixed model for handling semi-continuous longitudinal data and simultaneously modeling the multiple quantile functions in the presence of missing data. We use a 2-part model for handling excess zeros and use a multinomial probit model for handling missingness in the data. In this work, we did not consider, however, the problem of endogeneity and incompleteness in the covariates due to zero inflation. Our proposed approach is developed for univariate longitudinal outcome and cannot be simply extended for multivariate longitudinal outcomes containing excess zeros. Thus, it will be interesting to extend the proposed approach for a multivariate settings. That's it. Thank you.
Okay, thank you, Jayabrata. And I don't see any questions in the chat box yet, but I just request the participants, if they have any questions, I can just wait for 1 or 2 minutes. They can just type in the chat box. Anyone is saying something? Yes.
Sir, with kind permission from you, this is Shamim, a Commonwealth scholar, a chartered accountant as well from England. Right now, pursuing my research degree out there in the Metropolitan University. May I please ask my query to the honorable resource person, sir, please?
Sure, please.
Okay, thank you very much. Sir, first of all, my heartiest gratitude to you for this excellent lecture for us. Right now, I'm pursuing a CFA as well. So from that point of view, sir, unfortunately, as a business graduate, that much statistics and that much mathematics was not included, I mean, in our syllabus. But on the real world scenario, when you are making actually investment decision, particularly in the stock market, we need to actually apply them. So my heartiest gratitude to you for such an excellent lecture for us. But would you please be kind to provide us 1 or 2 reference books so that I can dig in personally about this topic and to learn more out of this thing? Thank you very much, sir.
Actually, I just I failed to understand your question is for which of the 3 speakers?
So I mean, right now, I mean, the model that sir has present.
Okay. So I think this is the questions for Joy brother, right?
Yes, yes, sir.
Okay, so if you kindly send your email ID to us, then we'll just send it to the speaker, and the speaker can provide you some references maybe.
Thank you very much, sir. Thank you very much for your cordialness. Thank you very much.
Okay, thanks. And I just have one quick question for Kiranmoy Chatterjee. So can you just give a general guidelines for the practitioners under what kind of situations the model that you proposed could be preferred compared to the existing models? Now, I understood the examples that you gave, but so is there any general guidelines? Because the kind of dependence that you discussed is very hard to guess actually before you have some kind of understanding of the data.
Exactly. Yeah, you are right. Actually, you can guess in some sense that whether your data have some list dependence or not. Okay, but you can guess through that if it's like if you are in a DRS dual system, then the joint cell, that means like X11, that means the number of people counted in both the list. Okay, so this kind of cell, these cells will be, the count will be larger than other cells. So those cells which are coming from more than one source, so if those cells are, the counts are larger than others, then you can guess that there is some sense of dependence, but that is not all time. So in that case, sometimes you have to check, you have to test that whether there is a dependence or not. And in this domain, what I have found so far actually for the human population, that means not much work has been done yet. That's how to identify that whether dependence is there or not, or if the dependence is there, then which kind of dependence? Is it positive dependence or is it negative dependence? Negative dependence means suppose you have captured in the first list, then if there is some kind of capture aversion in your mind, then you won't want to be captured again in the second list. So this kind of thing is called negative dependence. So what I have worked one time with Deonto sir also, that we have proposed a testing procedure to check whether there is a dependence or not, or if there is a dependence, then which kind of dependence it is. And if you are aware about, or by this kind of testing, that which kind of dependence is this, then there are some models in the literature, including our latest proposed models also, that you can use this data.
Okay, great. So since I don't see any further questions in the chat window, so I hope that there is no further questions from the audience. So I'll thank all the three speakers again for their excellent talk. And so by this, I basically end the session here. And our last session, which is the statistical challenges faced in the industry, will start from 6 p.m. So I request the participants to again join by 6 p.m. We'll have 4 of our experts from industry who will share their experience and will discuss on the statistical challenges that they're facing in the industry. So thank you very much, and we'll see you again at 6 p.m.
Hello, sir.
Yes.
Sir, if you please don't mind, I have a request. This is Shamim again.
Sure, please.
May I please? Sir, thank you very much. Sir, I mean, this FDP is really, really very excellent.